This section 2.3 on basic limit laws is a pretty short section, and we've actually already looked at most of these rules in previous sections, but we're going to kind of formalize them and get them written down in this section. This lecture will go quick, and so will the homework. First of all, the laws that we're going to be looking at are basically made up of limits of functions. Now, these functions can be constructed as either sums or differences. They could be multiples, products, quotients of other functions. So they're combinations of other functions that we're going to be looking at. So let's go ahead and look at the basic limit laws. The first premise that we look at when we're looking at the basic limit laws is the limit of each of the individual functions that make up the overall limit must exist. So the way we write that is we assume that the limit of f of x at some value of c exists, and the limit as x approaches c of some value of g exists as well. This is very, very important. So this assumption is very important, and we need to keep it in mind, because sometimes we'll come across a limit that'd be really easy to work with if these criteria weren't met, but they have to be met. So let's go ahead again and start looking at our basic limit laws. The first basic limit law that I want to look at is called the sum law. Now we'll write this out formally, but one way that we can remember it is to say the limit of a sum is the sum of the limits. And of course we can replace the word sum with difference here as well. Well, the way this formally looks then is the limit as x approaches c of some sum of functions, which is f of x plus g of x, and I'm going to put in the minus here to show that you could subtract here as well, is just equal to the sum of the individual limits taken separately, plus or minus, to show that I could be adding or subtracting here. So the limit of the sum is the sum of the limits. That's usually the easiest way to remember that. Also keep in mind that with my limit notation, I should have brackets or parentheses defining what exactly I take the limit of, but a lot of times we end up dropping that because that's all we're working with is the limit. We're not multiplying or dividing by anything. So it's clear that whatever comes after the limit is what we're actually working with. So let's go ahead and look at an example here. The example that we want to look at is the limit as x approaches 2 of x squared plus x. Well, what the sum law says, the limit of this sum that I have here is just actually the limit of the individual pieces. So the limit of the sum is the sum of the individual limits. And of course, to take the individual limits, I can just plug directly in and hope for the best. So I get 2 squared plus 2, which is 6. So therefore, the limit as x approaches 2 of x squared plus x is equal to 6. So that works out pretty easily. Now again, this also works for a difference. Second rule, this is going to be the constant multiple law. The constant multiple law basically says you can pull any coefficients out front of the limit, or factor if you'd rather say that. So you can factor any coefficients out front of the limit. And of course this has to follow all the mathematical rules. I can only factor out a coefficient if it's a common coefficient to every single term in my limit. And we'll look at an example like this. Okay, in general, this looks like the limit as x approaches c of k f of x. Now k is my constant here. What this is saying is I can pull k out front and then just take my limit as x approaches my constant of the function. So that's what that's referring to. Let's go ahead and look at an example for this case. The limit as x approaches 7 of 3x. Well, you already will just plug 7 directly in and say 3 times 7 is 21 and be done. And that's great. But I just want to show you what's actually happening here is you do factor that 3 out front and take the limit of what's remaining. So I end up with 3 times 7 here, which is 21. Now this 3 that I factor out has to be common to every term. This one's pretty easy to look at because I only have a single term. So you have to be kind of careful about that. For instance, if I had something like the limit as x approaches 7 of 3x plus 4, I cannot pull that 3 out front because it's not common to every term here. So this would not be true. The next law that I want to look at, let's scroll down a little bit, is the product law. Now those of you who have had some exposure to calculus before, this is not the product rule for differentiating. This is the product law of limits. This is similar to the sum. The limit of a product is the product of the limits. Okay, so let's go ahead and look at a generic definition here. The limit as x approaches c of two functions being multiplied together, function f of x times function g of x, is just equal to the limit as x approaches c of each of the individual limits. Now again, remember our rule up top. This is providing that each of the individual limits exists. If the individual limits don't exist, I cannot use the product law. Let's go ahead and look at an example representing the product law. Limit as x approaches 3 of x cubed times the square root of x minus 2. Well, again, usually you'd plug directly in here. You'd get 3 cubed is 27. The square root of 3 minus 2 is the square root of 1. And 27 times 1 is 27, and you'd be done. And that's fine to do, but I want you to see where everything is coming from here. So using the product law, this is actually saying the limit as x approaches 3 of this entire product is just the limit of each of the individual products multiplied together. So here I'd have 3 cubed. Here I'd have the square root of 3 minus 2, which would be 27 times 1, or 27. Okay, so again, and I know you're going to plug directly in, and that's a lot easier. It's just important to kind of know where these rules come from. Let's go ahead and look at our fourth law. Well, we've looked at sum difference, we've looked at product, so what we're left with is quotient. So let's go ahead and look at the quotient law. With the quotient law, what we're going to say is the limit of a quotient is the quotient of the limits. Okay, and again we'll look at this generically, and then we'll also look at a specific example. So limit as x approaches some constant of some function of x divided by some function of g is just equal to the limit as x approaches c of the numerator divided by the limit as x approaches c of the denominator. So we can look at these individually. Now again, this is providing that both of these limits must exist. Now in this case, if I get this denominator limit to be 0, I need to be careful. That might mean the overall limit is undefined, and it also might mean the overall limit is indeterminate if the numerator is also 0. So be kind of careful about those. Let's go ahead and look at an example. The limit as x approaches 4 of the square root of x over x squared minus 2. Well, I could put 4 directly in, and if I put 4 directly in, I end up with the 2 in the numerator and a 14 in the denominator, so I'd have 1/7. And again, this is what I expect you to do. But I want to also see exactly what rule supports this. So that's the same as taking the limit as x approaches 4 of the numerator, the limit as x approaches 4 of the denominator. So for here I'd have the square root of 4, and here I'd have 4 squared minus 2. So I have 2 over 14, which is 1/7. So that works out pretty slick. And again, I don't expect you to quote these laws. I don't expect you to necessarily, always write out every step, but know that they're in existence, and that's what makes the availability of just being able to plug in a number into a limit and get out a nice solution. I would like to look at some important examples before we end here. And these are basically examples that we want to be careful of. First of all, let's look at the limit as x approaches 0 of 1 over x. Now, there's a little bit more to be said here, but when I have x in my denominator, this is really x over 1, and when it flips, it would actually cancel. So I would get a 1 here eventually. But I would like to look at this a little bit differently. Okay, let's go ahead and end this lecture with an example that we want to be really careful of. In this particular example, when I plug directly in, I'm actually taking the limit of the numerator and the limit of the denominator. The limit of a quotient is the quotient of the limits. So let's go ahead and look at that. Well, if I plug directly in, I get 0 in the denominator. In the numerator, I get 1 over 0. This is undefined, and this violates that rule that we talked about up above. This violates the fact that each of the limits must exist. This limit is undefined, therefore the limit does not exist. And the rule says both of the individual limits must exist in order for these rules to apply. So I kind of have a little bit of a problem. I can't apply the quotient law. So what do I do? Well, we can look at this algebraically, which technically we haven't covered yet, but let's go ahead and have a look. Now the above did not say that the limit did not exist. It just said I can't apply the quotient law, so I'm going to have to come up with some other way to look at this, and we're going to look at this algebraically. So let's go ahead and look at the limit as x approaches 0 of 1 over x over x. Let's go ahead and look at this as a rewrite. Algebra, algebra, algebra. X is the same as x over 1. When you divide by a fraction, you're multiplying by the reciprocal. So I have 1 over x in my numerator, and then this value of x over 1 in the denominator flips to leave me with 1 over x. So this leaves me with the limit as x approaches 0 of 1 over x squared. Well, if I plug 0 directly in, I get 1 over 0, which is undefined. Therefore, the limit does not exist. So that's the correct solution here. Now you might say, well, wait a minute, why didn't we just come up here and when we got d and e in the numerator, just say the limit didn't exist? The quotient law does not say that. The quotient law says in order for the quotient law to work, both of these have to exist. And the numerator portion didn't exist, so I can't use the quotient law, so I need to go to somewhere else to try and come up with a solution. So these questions are usually pretty short. You're usually just plugging in some numbers, sometimes doing a little bit of simplification and factoring, but this homework should go pretty quickly. Also, it's a good idea to have Maple open. When you have Maple open, you can go ahead and look at some graphs and also use Maple to solve your limits in order to see if you got the right answers as well.